Okay, thanks a lot for this very generous introduction. I'm really happy and excited to be here. As you know, Surajit sir knows that I'm very interested when it comes to teaching physics and sciences and about my field. So I'm really happy to be here and I'm glad to be invited. So let's get started. I'll just share my screen now. You should be able to see my screen. Is the screen and the cursor everything visible? All right. All right. So let's get started. So, what I'm going to do today is basically start off with a pedagogical sort of talk on quantum machine learning, and we'll explore the current landscape of quantum machine learning and chart the territory, take you from algorithms to architectures. And what these terms mean, we will see as we explore. So the first part of this talk will be mostly a pedagogical one, where I explain what quantum machine learning is all about and what we can do with it. The next part, when I go from algorithms to architecture, it will be a bridge to the kind of research that I'm currently doing as a PhD student at UPC Barcelona Tech. So let's get started. So to start with, I want to give those in the audience, especially the students, some fundamental background on quantum computing. As we know, that traditional computers that we see around us operate on binary logic using something called bits, where the system or the bit can be in either zero or one state, and they can only exist in one state at a time. However, quantum bits or qubits, which are employed in quantum computers, can exist in zero and one state and also in a superposition state. So the picture that you show here is an artist's representation of something that's called a block sphere, where the position of a point on the surface of a sphere describes the state of a two-level system or a qubit. So you can see that there are infinite number of points and you have an infinitely large state space for a qubit. The another property of these qubits is that although they exist in superposition, once you measure them, you collapse them into either the zero or the one state, which you call the computational basis states. And other than that, other than superposition, qubits exhibit interference and entanglement properties. Entanglement meaning that the states of qubits can be correlated regardless of the distance, and any influence or interaction that one of the qubits has affects the other. So mathematically, you can see that the state of a qubit is represented as a linear combination of the zero and one states, and the square of the absolute values of these amplitudes, alphas and betas, sum up to one. So this is pretty basic. So moving on to one of the most important concepts in quantum computing is the quantum circuit. So the picture you see here is a quantum circuit diagram, which represents the temporal dynamics of qubit states. The horizontal lines that you see here represent all the qubits that you have in your system. And the blocks, the colorful blocks you see here, are unitary operators that evolve the states of qubits, and they are called quantum gates. So you can see there are gates that act on just a single qubit, and there are gates that act on multiple qubits. And these are called entangling gates that can create or destroy entanglement existing between qubits. So the important thing to note here is that time flows from left to the right. And in typical quantum algorithms, what you have is that all the qubits are initialized to the zero basis state. Then you have a bunch of unitaries acting on the qubits. All the gates inside block A is applied in parallel. And then in the next time step, or something that I'll refer to as a time slice later on, um, everything in the next time slice is implemented in parallel, and then you measure. Upon measurement, all the states collapse to zeros and ones. So at the end, you have a bit string. So sometimes in certain quantum algorithms, this bit string after a single measurement is the inference or the result of your quantum computation. And sometimes you need to implement the same circuit again and again to build a probability distribution of all the basis states, and the probability distribution is essentially the solution of your computation. So this is what a typical quantum algorithm looks like. So having said that, what quantum computers can do for us is that they can potentially solve classically intractable problems which are otherwise not solvable on efficiently solvable on regular computers that we have today. However, quantum states are very fragile, which leads to quantum noise. For example, in a two-level system, the system will always try to decay from the higher energy state to the lower energy state. So we have a decay. We can also have decoherence when your qubit interacts with the rest of the environment and loses the quantum information. Apart from that, there exist other kinds of errors. For example, gate errors. When you want to apply a particular gate to a qubit, but the gate is spurious or erroneous. And then you have something called state preparation and measurement error, or spam or crosstalk, which means that you want to address one qubit, but the neighboring qubits are affected. So all these sources of noise lead to corrupted or incorrect computations. And for practical applications, you need QAC, or quantum error correction, to correct for these errors, which requires a large number of high quality qubits, millions of them. However, current hardware only supports up to 100 to 1,000 low quality qubits. This is the state of the art right now. And we use the term NISQ, or noisy intermediate scale quantum computers, to refer to the computers that we have today and the ones that we'll have in the immediate future. So this is the background on quantum computing I want you to have, because this will be interesting as we move along. So the other background that I want you to give is classical machine learning, what machine learning is all about. So you may have heard a bunch of terms like AI, machine learning, and deep learning, and it's not always possible to clearly distill the differences between them. So AI, or artificial intelligence, stands for machines or computers performing tasks that are usually associated with human intelligence, such as learning. You learn from previous experiences, and based on that, you know how to act in unknown and new scenarios. This is called learning. And then you have reasoning. So maybe you're familiar with the new rise of these AI models like DeepSeek R1 and ChatGPT's new O3 and O1 models, and they're all reasoning models, meaning that instead of giving you an answer to a particular text prompt, they will also explain the reasoning as to how they solved a particular problem. So this is also something that AI is all about: problem solving and perception. Perception means that you sense your environment, and based on that, you act. So this is kind of in the purview of IoT devices with AI-enabled stuff and robotics. So this is all about AI. A subset of AI which only deals with learning is called machine learning. And loosely speaking, machine learning means learning patterns in data. So what I do is provide the computer with a bunch of data, let's say pictures of cats and dogs, and it learns the patterns that are common among the pictures of dogs and common among the pictures of cats. So what you expect is that when you show it a new picture, it will be able to tell whether, based on the patterns that it has learned, whether it's a picture of cat or a dog. And a subset of machine learning is called deep learning, where we only use a specific architecture. I'll explain this later, called neural networks. And this is the most popular approach to machine learning. For example, LLMs such as ChatGPT, they all use neural networks. They're based on deep learning. This brings us to quantum machine learning, which is a combination or an amalgamation of machine learning and quantum computing. And how do you combine quantum computing and machine learning? As it turns out, there are four approaches as well as four ways to categorize quantum machine learning proposed by Maria Schuld and Patricioni in 2018. And it depends, and there are four categories depending on the nature of the data and the nature of the processing device. The first block here, the CC, stands for the situation when your data is classical, taken from the classical world, and you use a classical computer to learn patterns in them. It's just that the algorithms are inspired by quantum computing. These are called quantum inspired algorithms. So they can also be called quantum machine learning. I personally don't think it's a good use of the term, but it is what it is. Then you have a CQ, which refers to the situation when the data you have is quantum, meaning the results of, let's say, a quantum experiment, and you use classical machine learning to process it. It can be the situation where you use classical machine learning models to classify quantum phases of matter across a phase boundary, and this is also categorized as quantum machine learning. But the one that I personally believe is a good use of the word quantum machine learning, and most of the community refer to when they talk about the term QML, is the situation QC or QQ, when your data can be classical, like pictures of cats and dogs, or the results of a quantum experiment, quantum data, but you process them using a quantum computer. So, in true sense, as it involves the use of a quantum computer, these two, QC and QQ, are quantum machine learning. So, now I want to introduce you to certain quantum machine learning models, particularly the support vector machine. So support vector machine is a classical machine learning model. They're called SVMs. They're linear models that perform binary classification, again, with reference to pictures of cats and dogs. What I want to do is that I want to classify or distinguish between pictures of cats and dogs. So what we do in machine learning is that the data we give to the computer or the model has a lot of features. For example, pictures may have, let's say, a lot of pixel values, the color saturation, and brightness, and everything. These are all features, and they are represented in a certain dimensional Euclidean space as vectors. So all your data is converted into vectors. So the picture on the bottom left, you see, it's here, it's just for convenience. Typically, you can have a large number of dimensions, but here you have two-dimensional data, meaning data that has only two features. And the features are represented in the X and Y coordinates. And here you have two types of data that are labeled as red and blue. So you can think one as the pictures of cats and the others as the pictures of dogs. So what support vector machine aims to do is that it will find a linear decision boundary, which is a linear hyperdimensional plane in that hyperdimensional space, um, that can be used as a linear decision boundary, so that when I introduce a new point, it can tell based on whether it is on one side or the other, whether it's a picture of a cat or a picture of a dog. So this is how this works. And to train this model, what we do is that you start off with an arbitrary hyperdimensional plane, and your goal is to maximize the distance between the plane, which is depicted in this solid black line, to the distance between and the distance between that plane to the blue and the red points, to the two data points on both sides. You have to maximize this distance, also called the support vector. So this can be represented as an optimization problem on the top right, where you minimize this W, the norm of W. W is basically the normal vector to the hyperdimensional plane, and subject to the constraint that the data of one particular type of data is on one side of the hyperplane and the other type of data is on the other side. So Y's are basically labels that tell you, okay, it's one kind of data or the other, picture of a cat or a dog. It's a label. And X's, XJ's are the data points, all these points. And epsilon is just to leave room for some error. So as you can see, we start off with a randomly initialized hyperplane, and we solve this optimization problem in iterations, which the process is called training, so that we maximize this distance of the gray region over here. So it is a very complicated and a computationally intensive process. It can take up a lot of computational resources, because you see, in when you have a large dimensional feature space, by which I mean when you have a large number of features for all your data points, uh, calculating these numbers can be really computationally intensive. So there's another approach to solving the same optimization problem, which does not directly involve the use of a separating hyperplane. It is called the Lagrangian dual of the same optimization problem, where you don't have the W term for this hyperplane. What you have instead are the inner products, or some sort of distance or similarity metric between all the data points, xj's and xk's, some distance matrix between all the data points. So why is this useful is what I'll explain later. So with the support vector machine, we have something called kernels. So consider the situation where your data is not linearly separable. For example, on the bottom left, you see data which is only one feature, meaning the feature space is one dimension. All the data points are represented by just one number, x. And you can see you cannot have a linear decision boundary. You cannot say, okay, all the values right to this belong to one kind of data, and all the values left of this belong to the other kind of data, because that's not the case. However, what we do when the data is not linearly separable, you project the data from a lower dimensional space to a higher dimensional space. For example, here from x, we convert it into x comma x squared, where you can see now you have a two-dimensional feature space. The x coordinate remains the same, but the y coordinate is now x squared. And in this higher dimensional space, you can find a linear decision boundary that separates two different classes of data. And this transformation or map is represented by phi, also called a feature map, and it takes your data from lower dimensions to a higher dimension Euclidean space. It's important. And to solve this, and when you have a very large dimension, this like in real scenarios, you'll never have two-dimensional feature space. It can have like you can have thousands of dimensions, tens of thousands of dimensions, millions of dimensions, even infinite dimensions. So in very high dimensional spaces, solving this is very difficult because you have so many dimensions and your computer can't keep track of them. And taking inner products is also inefficient because you have so many dimensions. But sometimes when you have specialized or specially structured feature maps, then this inner product, which is represented by phi of x, inner product with phi of y, is efficiently computable in the form of a simple function of x and y. It can be something like a negative exponential of the difference between x and y, something like that. So sometimes when you have specific feature maps, this similarity metric or the inner product, which we call kernel between the two data points x and y, is efficiently computable. So to sum things up, whenever your data is not linearly separable, you project it into a higher dimensional space with the hope that in this higher dimensional space, it is linearly separable. And in this higher dimensional space, you can compute inner products efficiently. So these are the two conditions that you have. So this is a very common way to do solve classification problem. It is used in support vector machines. And once you have inner product, you can use the Lagrangian dual training form to classify, to learn from the data. Now, what can quantum computing do for us? So as we know that the dimensionality of the Hilbert space increases exponentially in the number of qubits. So in quantum computers are inherently high dimensional. So it makes sense to use quantum states as feature maps. So what we do is perform a quantum feature map, where instead of taking your data vectors from one small dimensional Euclidean space to a higher dimensional Euclidean space, you map it into a very high dimensional quantum state in the Hilbert space. So you see psi of xi, meaning that the quantum state depends on the data point, and it is usually accomplished by the application of an unitary u of f, which depends on the data itself, which is applied on the all zero states, where all the qubits are in the zero states. So this transformation is something that we call a feature map, akin to classical ones. And the circuit that you see here, it starts off with all zero states, and you apply the feature map corresponding to one data point, and that accomplishes the task of embedding or encoding your classical data onto the Hilbert space, or making it into a quantum state. That's it. That's the purpose of the green block here. But to solve the support vector machine training problem, what we need to do, we need to find inner products or compute the kernels. So the kernels between two data points I and j is computed by, again, a similarity matrix, which we take as the trace inner product or the Hilbert-Schmidt inner product of the density matrices corresponding to the quantum feature maps of two data points xi and xj. And it's simple linear algebra. If you just do it, if you take into account that everything inside traces, you move them around, you get the final expression. What this means is that you start off with all zero states, apply a feature map corresponding to one data point, and then you apply the inverse of the same feature map, but corresponding to a different data point, and you measure it and you calculate the probability of obtaining all of them in the zero states, all the qubits in the zero states. That probability is the value of the kernel between the 2 points. So once you have the kernel, you can go back to the Lagrangian dual and solve the classification problem. So you see that quantum support vector machine is not entirely classical. You just compute this inner product or the kernel using the quantum computer, but the training, the solving of the optimization problem is entirely classical. All right. So this is one of the most important models that I talked about, quantum support vector machines. The next model I want to introduce is classical neural networks. So just like any networks, you have a bunch of nodes, which we call neurons, and a bunch of edges connecting them, which we call weights. So what we have on the very left, we input all the features of the data on all the input layer of neurons. And then you have a bunch of edges which have some values, weights, which are multiplied to all of the input values and taken to the next layer of neuron and summed up from the contributions of all the previous layer of neurons. And you apply a nonlinear function on top of it, and you do that layer by layer. So what this is basically you have a bunch of matrices, weight matrices, and some nonlinear functions interleaved between them. And the goal is to compute a cost function at the end of it. The input is the data and the output is your inference, or saying whether the input data is a picture of a cat or a picture of a dog. And the cost function is a function that you construct which measures the distance of your current inference from the actual value that it should be. And the goal is to change the values of all these weights. By the way, in this picture, you see some lines are colored blue. Blue means that the weight is negative, and red means that the weight is positive, and the intensity of the color represents the value of the weights. So your goal is to train the model by changing by varying the value of all the weights so that the cost function is minimized. So this is what traditional neural networks are, and now we do it in quantum. So of course, as I said, we have a bunch of weight matrices with nonlinear activation functions interleaved, which is basically just linear algebra. And we know linear algebra is the language of quantum mechanics and by extension, quantum computing. So this is the circuit of a quantum neural network. You start off with all zero states, as is customary. You encode the data by the same feature map that I described before, which depends on the data X. And next to it, you have this red block, which we call a parameterized quantum circuit. We can also call it the ansatz, or we can also call it the variational form, which depends on a bunch of parameters theta, which we can also call trainable weights. And then we measure all of them to compute the expectation value of a particular observable. So your inference is this, a function depending on the data and the parameters, which is the trace inner product of an observable with respect to the density matrix, which is basically just the expectation value of the operator. Okay, so this expectation value is your inference, and based on that, you make cost function, and your goal is to optimize the values of the theta so that the cost function is minimized. Okay. Uh, unfortunately, unlike classical neural networks, the only non-linear operation we can have in quantum computing is that of measurement. So measurement, you can think of this as a non-linear activation function, although this is not correct in this particular example, but we can talk about this later. Um, so this is what a quantum neural network is. So I have talked about these variational forms and feature maps, but I did not describe what they actually look like in terms of the actual. Does anyone have any questions? I'm hearing some pop-up sounds, but
Yeah. I have one very small question. That is that unitary operators what you have constructed.
Mhm.
These actually consists of this neural networks, layered neural networks or something
No, no,
like
no, no.
this.
These are just quantum gates, a bunch of quantum
Right.
gates. I described them what they are.
Okay. but whenever you will frame your algorithm, that is neural
Mhm.
network based algorithm, so where these neural networks will come?
So no. Classical
This
neural networks don't come. This is a quantum algorithm or a quantum circuit, and we call it a quantum neural network. Because just like neural networks, you have the data which
but you
goes
don't
in.
have any layered structures of neurons like this.
Oh, no. We do actually. We do the variational form. I have described them as a single black box, but inside this,
Yeah, it's a
you'll
black
see a
box,
layered
right?
structure.
Yeah.
Right? It's a
Okay.
black box, but I'll describe what's inside those black box
Yeah.
in just a minute.
Okay.
So
Okay.
So the first part, which we refer to as a feature map, is also called data encoding or data embedding. It's how you embed the classical data onto the quantum state. And the first way to do it is angle encoding, where you start off with the zero states and you apply a bunch of poly rotations to all the qubits. Here we applied the poly x gates, which is parameterized by x1, x2. And these x1, x2s are just the features of the data, of the input data. You can also apply the rotational y gates or the rotational z gates. You just have to be careful that when you apply rotational z gates, you have to put a Hadamard because zero state is an eigenstate of the rotational z operator. So this is the different types of angle encoding that you do. And then you have something called amplitude encoding. Okay, one thing about angle encoding to notice here is that the number of features of data x1 all the way up to xn, n number of features, is equal to the number of qubits in your system. So it's not that qubit efficient. Uh, on the other hand, you have something called amplitude encoding, where you create a quantum state such that the amplitudes corresponding to the different basis states is represent all the features of the data. So as you know that the dimensionality of the Hilbert space grows exponentially as the number of qubits, so the number of qubits will be logarithmic in terms of the number of features. So it's quite efficient in terms of the number of qubits. It's also inefficient in terms of other quantum resources, which I don't want to get into. This is also the reason why I did not draw a circuit diagram for this, but we can discuss this later. And then you have something which, in my opinion, is the most commonly used feature map, which looks very similar to angle encoding. It's just that you have a bunch of C0 gates and some rotational Z gates in between. So why is this the most popularly used feature map in quantum computing? Is that when you build quantum support vector machines using the ZZ feature map, you can show that for certain highly structured synthetic data with no real world applications, this feature map and the quantum support vector machine you construct with it can outperform any classical algorithm in binary classification tasks. So that concludes data encoding and feature maps. And then we come into the circuit architectures of the variational forms or ansatz. So this is the layered structure that sir you had pointed. So this is what is inside the red box. You see these layered structures. The two local onsets consists of a bunch of trainable rotational gates thetas
Okay.
and two qubit gates interleaved between them. And then you have something called highly entangling layers, and this onsets can create really very highly entangled quantum states. And then you have something called tree tensor network. It's inspired by tensor networks. And you can see that the number of single qubit gates and the number of two qubit gates decreases halves with the number of layers. And at the end you just have one CNOT gate and one rotational gate, and you measure just one qubit. So this is particularly good for binary classification problems. And one of the things that you'll notice that it is that the number of layers, which I'll also refer to as the number of time slices, is logarithmic in the number of qubits, and this will be important for what I'm going to tell later. So that's what the different models, the most popular models look like, but now we go into training. So I've described that the goal of training is to minimize the value of a cost function, right? But how do you do that? How do you know whether you have to increase the value of your parameter theta or decrease the value of your parameter theta? You do that by computing the gradient of the cost function with respect to the trainable parameters and moving along the direction of the gradient in iterations until the gradient becomes zero. at which point you are likely at a local minimum, which is the solution, which means your model is trained and is ready for inference on unseen data. And one of this, according to me, is one of the most beautiful results we have in the field of quantum machine learning. And this is this very simple formula for the gradient of the cost function. You just have to calculate the cost function at two differently offset values of the parameters, namely theta plus pi by 2 and theta minus pi by 2. And you have to implement the same circuit twice, calculate the expectation values, calculate the difference between them and half them, and this will give you the exact value of the gradient. So this is something that we don't see in classical machine learning, but the formula is very beautiful in quantum machine learning. And so this is the gradient that you compute, and based on this you can train your models. But the problem with training quantum machine learning models is as follows. The picture on the left depicts that as you increase the number of qubits on the x-axis, the variance of the gradients diminishes exponentially. Notice this is a logarithmic scale. And the same happens as you increase the number of layers. The gradient of the variance diminishes exponentially. And it actually does saturate for by the way, different colors indicate different number of qubits. Here we are just seeing the variations of the variance of the gradient cost function gradients with the number of layers, and all of them diminish exponentially. What this means is this. So you start off with a smooth cost function landscape, the picture on the top left with the one depicted in blue. Once you increase the number of qubits, your cost function landscape becomes very narrowly concentrated, meaning if you initialize the parameters anywhere except the very close vicinity of the minima, the gradients will be zero. So you don't know which way to move, which way to train your model. So that's a problem. Your models cannot be trained, and this is called barren plateaus. You can circumvent this only if you get lucky and your initial guess is very close to the vicinity of the actual minimum, which is not always a guarantee. In fact, it is never a guarantee. Okay, and another thing is that the more noise you inject into the circuit, the more is the occurrence of this phenomenon, barren plateaus. So this is one of the biggest problems in the field of quantum machine learning, and there are many ways to circumvent it. The most popular one is the one on the bottom left. So whenever you have a quantum circuit, the depth of which, or the number of time slices of which, is logarithmic in the number of qubits, and you have local cost functions, meaning that you don't measure all the qubits, you measure only a subset of them, you don't have cost function landscapes. I can explain why this happens later, but if you compare these three circuit architectures, you'll see that these band plateaus occurs in two local and highly entangling layers, but not in tree tensor, because the number of layers is logarithmic in the number of qubits. That's the reason we don't see band plateaus here, and that's why tree tensors are very important. All right. So this concludes, you know, machine learning, most of the machine learning literature that is out there, and most of the pedagogical part. But I have shown to you quantum support vector machines and quantum neural networks. By the way, the term QK is just quantum support vector machine. It's just another fancy name for it. But there exist other models, and we categorize them broadly into non-variational models and variational models. The ones that are non-variational models, they're mostly based on linear algebra methods, which we call QBLAS, or quantum basic linear algebra subroutines, which are based on the famous HHL algorithm. And they are very well-structured algorithms for well-defined problems with known complexities. However, they're not suitable for the kind of quantum computers we have today. We need high quality qubits and large number of them to implement them. And on the other hand, we have variational models, which are mostly quantum neural networks. But unlike non-variational models, they are heuristic, meaning that you cannot prove any advantage. You can just say, okay, so your problem has blah 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 structure, your neural network, quantum neural network, has blah 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 structure, so maybe your quantum neural network can show us some advantage. So but it's all based on heuristics, and fortunately they are implementable on the NISQ devices that we have today. So that's a taxonomy of quantum machine learning model. It's a very broad, and I'm not going into the details of this, but that covers the landscape of quantum machine learning models, aka algorithms. So this sums up the algorithms part, but what is architecture? Now, to understand architecture, we need to understand what a quantum computer system is all about. At the very top, you have quantum algorithms, which is the models that I showed you before, which exists only at a logical level. And at the very base level, inside a dilution refrigerator at millikelvin temperatures, you have the qubits cooled to deep cryogenic temperatures. You have the hardware, and then you have the control electronics, which will send microwave pulses, which apply gates on the qubits. And in the middle, you have something called microarchitecture and compiler, which converts the quantum algorithms into the language that is native to the hardware, into the pulses that the qubits can process natively. And you also have a quantum error correction layer, which corrects for all the errors. So you'll see a lot of stacks. So this picture is what we refer to as a full stack system architecture, because all of these are layers of the stack. Quantum computer architecture refers to the interplay and co-integration of all these layers of the quantum computer system, namely how quantum algorithms are interacting with the compiler and how the compiler is interacting with the control electronics and which is interacting with the qubits, how they are working in unison to give you some really good quantum computation. So this is what quantum computer architecture is all about. It is also about the co-design of all the layers, meaning that if you ask me to build a functional, very highly functional quantum computer system, um, I won't just give you highly optimized quantum algorithms. I'll also give you highly optimized qubits and control electronics and compiling methods, and I'll optimize all of them together, not one at a time, but all of them together. So this is something that we refer to as co-design of all the different layers of the stack. And loosely speaking, quantum computer architecture is the interplay of software and hardware and how both of them work together. So let's just to give you an example, to give you a concrete example, let's just focus on one layer of the stack, compiler. So this is something that lies in the middle and most people don't talk about. So let's get into this. So on the top left, you see something called a coupling map, or you see four qubits connected to each other on a quantum processor. This is called a coupling map. This shows the real connectivity on the processor. And you want to implement this very circuit on top of it. The first thing that you do is called mapping. You map the logical qubits, the small q's, to the physical qubits on the actual hardware, the capital q's. And the mapping is quite trivial. You just map the logical qubit number 0, or the virtual qubit number 0 to the physical qubit number 0, and then you perform all the gates. But unfortunately, in superconducting and semiconducting spin qubit architectures, you won't be able to apply these gates marked in red. Qubit 1 and qubit 2 do not have any physical connectivity between them. That's why you need to apply a swap gate to swap the states between qubit 2 and qubit 0. And then you can implement the circuit by applying these two quantum gates. Okay, so what this does is that what I want you to take home is that you don't implement the quantum circuit that you want to implement. You respect topological constraints of the hardware, and you insert a bunch of other swap gates. These gates have very high latency, are one of the most expensive operations in terms of noise they induce. So typically in quantum algorithms, most of the noise and most of the bottlenecks come not from the structure of the algorithm, but from the extra swap gates that you add. So it's always up to the compilation method, compiling algorithm, to minimize the number of the swap gates. So this is one of the goals that you have while designing a compilation algorithm, and it's an NP-hard problem, meaning you only have heuristic methods. You cannot know whether you have an ideal solution. All right, so on the bottom, what you see on the y-axis are the physical qubits, and on the x-axis are different time slices. And the colors, the white and red colors, show at which time slice which particular qubit is active, meaning that a gate is acting on them. So as you can see in different topologies like star topology, heavy hex lattice topology, which is IBM's hardware, and square lattice topology, I won't explain what they are, but these connectivities of the physical hardware on the processor, you have different type of like spatio-temporal distribution of the qubit activations. And your goal is to not just to minimize the number of swap gates, but also to take into consideration whether you have any local hotspot or a bunch of qubits where you apply all the operations and the other qubits are sitting. So you don't want that. And also you don't want all the operations to be focused around a bunch of time slices, which you can call, let's say, a temporal hotspotness or a burstiness, if you will. Uh, so your goal is to minimize them, and the compilation has to take care of all of them. So there's a lot of optimization needed to be done. Next, I want to introduce something called modular quantum computers, which is actually one of the, let's say, the heart of the research that my group does. So what the quantum computing community largely is looking at, and what we are also looking at, is to propose a multi-core or a modular quantum architecture, which marks a departure from standard architectures where we put all the qubits on one chip. Now we have multiple chips represented by all these gray blocks or gray tiles over here, which we call cores. And each core is like a standalone quantum processor in itself. You have qubits on them, and you have to ensure that the qubits in one core can talk to qubits in another core. So you have to have some quantum coherent links capable of quantum state transfer. And for some temporal orchestration, spatio-temporal orchestration, you need some intercore controller and router. One of the things that we propose, and it's actually an elephant in the room as far as the progress on this project is concerned, is that we want to offload some of the routing and orchestration to a cryogenic wireless classical network on top of the chip. It's a technology called wireless network on chip that we are proposing, the first of its kind. And we also are betting on another technology called cryogenic control electronics, once in red. So if you look at quantum computers that we have today, you'll see a small quantum computer which has 2, 5, or 7 qubits, but it requires entire room's worth of control electrons and a lot of wiring. Like if you go to like any optics lab, you'll see that, right? But in quantum computing labs also, you'll see all these wiring control just 2 qubits. And the question is, when you have, millions of qubits, you have a wiring bottleneck. How are you going to pack all these wires on them? So the solution to that is actually something called cryogenic control electronics, meaning cryo-CMOS technology, electronics that you can co-integrate on top of the chip that leaves no physical separation between the qubits and the control electronics, so you don't have the wiring bottleneck. So this is a technology that is mostly researched by colleagues at particularly Fabio Sebastiano. You may have heard his name. He's also one of our collaborators, and that's why we want to propose this technology to scale. However, the state of the art is that all the cryogenic control electronics need for operating quantum computers, uh, they operate all the way up to 1 Kelvin, which is good for silicon spin qubits, but superconducting qubits who operate at like 10, 15 millikelvin. So in a dilution refrigerator, the physical separation between 1 Kelvin and 10, 15 millikelvin can be up to 1 meter. So the wiring bottleneck still persists. So this technology needs to improve, right? So that's what I wanted to introduce, because this one of the focus of my group's research and the an European project that we are most actively involved in. And once you have multi-core, the compilation layer, not just compilation layer, all layers are affected of the full stack. But I'm focusing on compilation layer, but because now the most expensive operation are not just swap gates. The most expensive operations are communication and the gates that you apply between 2 different cores, which we correctly assume. And here, what this shows is that you have a bunch of algorithms: quantum Fourier transform, concurrenter, quantum volume, random circuit, Draper adder, and the different colored lines show different compilation method. And the goal is to use the best compilation method, which reduces the uh, number of non-local communications. So this is what it is. So see, designing a quantum computer system is non-trivial. because you don't just optimize quantum algorithms, you optimize the compiler, microarchitecture, control and readout electronics, the qubits. I only show you the compiler for as a concrete example, but you have to optimize all of them. So the way to do it is that you take a bunch of metrics from all these different layers which characterize the performance of all these individual layers as standalone layers, and then you cast them into a single figure of merit, tau, as you see here. And then the goal is you explore the parameter space, which we affectionately refer to as design space exploration, and you trade off some parameters at the expense of some other parameters, and you reach a global maxima for the single figure of merit. And we say to the experimentalist, look, these are the different parameters for which you have the most optimal configuration of the entire quantum computer system. So this is something called design space exploration, and it's nothing unique to quantum computing. It's done for designing cryo CMOS chips and like regular chips and any kind of complicated system. You design them using this type of method. So to sum up, this is what my research looks like. Only that the quantum algorithms that I focus on are specifically quantum machine learning algorithms. I optimize the algorithms, the compiler, the control electronics, and the qubit so that the entire system is optimized or the most performant for quantum machine learning algorithms. So this is basically the pitch of my PhD research. We want to build something called uh, quantum machine learning accelerators. We know that we have deep learning accelerators, classical computing, domain-specific accelerators. Specifically, with accelerators, we won't have large language models as we have today. So this is what I want to do in quantum machine learning. So this sums up everything, and I think I've taken you through the landscape of quantum machine learning, both from an algorithmic and an architecture perspective. So thank you for this opportunity, and now I'm open to questions.
Yeah, I have a question. I
Yes.
mean, but I have slide-wise questions. So you go to the first
Yes.
slide.
First one.
The first one. I'll tell you which slide I want to. Okay, go to the next. Okay, this one. Explain a bit about. No, not this one. This one, I think. Yes, this one. Please explain once again last point. NISQ. Noisy intermediate scale quantum is something. You just
Yes.
elaborate.
Okay, of course. Basically, practical applications, you need something called error correction to correct for errors. A large number of high quality qubits, need millions of qubits. However, current quantum computers only have from 100 to 1,000 qubits, which are relatively low quality. So that's why we use the term noisy intermediate quantum computers to refer to quantum computers that have relatively low number of qubits of low qubit quality. So these are quantum computers that we have today and we'll have in the intermediate scale future. So
Okay.
you see, they are noisy, right? They are noisy quantum computers and they are intermediate scale, meaning you have not reached a million qubits. You only have reached 100 to 1,000 qubits. That's what this term entirely means.
That means by NISQ, you actually referring the 100 to 1,000 qubits of low quality.
Yes, not like these are not exact numbers. I'm referring to
Approximate numbers.
yeah.
Okay. Go to the next slide.
Yes.
Next. Okay. There is in the right hand side the table that you have shown CC, CQ, QC, and QQ. So I'm referring to the cell number 1, 2, CQ.
Okay.
So you are saying that the data is quantum being simulated in classical computer.
Yes.
Okay, so I have a little bit doubt over here regarding this particular cell. That once I read the Feynman papers on simulating computer, which is available in archive, and so far as I understood the paper, he said that quantum mechanics cannot be simulated in classical computer. So is CQ is viable? I mean, Rest of the CCQ, CQQ, I do not have any problem, but CQ, I am telling, is it viable? I mean,
Okay. Okay. So CQ is not the simulation of quantum systems. That's not the simulation. The data is generated from a quantum experiment. The data can be classical. The data is not quantum states themselves. They are the results that you get after performing a quantum experiment, the results that you can put on a lookup table, data, numbers, values of some matrix, right? And you use classical machine learning to process the data, as in say, okay, the results of this experiment means that this shows the existence of this particular quantum phase, where in a different experiment, in a different experimental configuration, a different data, the data is classical after measurement from a quantum experiment, and I process the data and I say, okay, this corresponds to different quantum phase of that. Okay, so this is nothing new or uncommon or something that cannot be done. People do it a lot. Uh, I think this is very common. People study, the jets in high energy physics when particles collide and jets of high energy particles are emitted. People classify the jets in machine learning models, classical machine learning, right? Yes. Yes. Mhm. Mhm. Yes, absolutely. Yes. Yes. So, to answer that question, yes, I agree that from a very reductionist perspective, if you reduce everything down to the absolute nature of the data, I'd agree that CC and CQ are equivalent, but like what defines CQ and distinguishes it as from CC is that you are trying to process the purpose. Basically, the problem is different. The problem is different. You are no longer classifying pictures of cats and dogs. You're classifying different types of particles. And additionally, I agree with you. And I personally, and you're actually asking the wrong person. You should ask Schuld and Patricia. And I personally don't think it's an abuse of the term quantum machine learning. I personally think QC and QQ is um, actual quantum machine learning, and my research involves only these. So I don't know why they put it like this, but yes, it's true that in the community, people still use the term QML for something that does not involve a quantum computer.
okay, so um,
Mhm. True. Absolutely. Yeah, yeah, true.
so my third question has already been asked by Atanu. I was about to ask you about the difference between CQ and QC, because in this matrix, the second row is important for us. First row, I don't find any interest in CC and CQ.
Yes, me neither.
Yeah, actually, so it has already been asked by Atanu. Acha, one thing you could tell me, how much people have to wait to get complete QQ? How many years?
People do it even today, actually.
Yeah, but in lab. not
Yes, in lab, actual
lab.
lab
Lab. But
simulations.
just if I if I try to connect with the history of classical computer from theory to the desktop, then I'm just asking that question. Your assessment of